Hello and welcome to Toddcast number 34. We're just kind of flying along through these. This is the start of what corresponds to chapter 8 on the syllabus. So we're starting into addition reactions. And best thing to do when start into it is just say the name generally gives away what's going on. So just like we mentioned, substitution reaction, one group substitute for another. Elimination reactions, we eliminated two groups, usually leaving group and a hydrogen on neighboring carbons. When those left, the electrons are left behind, formed a pi bond between those two carbon atoms. And so we're continuing that same route, only this time we're doing essentially what's the opposite of elimination. So elimination, you take an H in a leaving group, they leave, and the electrons left behind, like I said, from pi bond. This one, we're going for the pi bond. We're now actually going to add, initially we'll do an H in some other group, but it's going to be adding two substituents, two atoms to the carbon-carbon double bond. So this, I want to start with the simplest cases, and we'll go into a little bit of the mechanism to explain it, and then we'll go into more examples of it, and then go back to the mechanism. We're going to try to build the mechanism for the reaction, how it goes, and the preferences for the reaction simultaneously. And so, as mentioned, we have two carbons, and I've intentionally chosen an example here where the right carbon, could have been left, but I chose the right, has bulkier groups. So it has two CH3s attached, whereas the left carbon just has two H's. So one side is less crowded, easier to get to than the other side of the double bond. So I chose asymmetry, so we're going to identify where things go. And so I actually want to start out with a mechanistic thought first before going into the actual reaction. So the mechanistic thought is this. We always want to have electrons going from where they start to the most preferable spot to be. And so if I look at an HX, and assuming this is a halo acid, but in reality it could be H connected to any good leaving group, so it could be nitric acid, sulfuric acid, some sort of acid, but H and whatever this group is. And the way it's set up is the H, because it's less electronegative than whatever it's attached to, will carry a delta plus, and the other group, whatever it is, will carry a delta minus. The electrons, the nucleophile in this group, will actually be the most available pair of electrons, which unlike what you don't normally see, normally look for a lone pair, no lone pairs on H's, no lone pairs on those carbons, no lone pairs on those H's. So it's the most readily available pair of electrons, which is the weakest bond, in this case, the pi bond. So the pi bond is going to be our nucleophile, and if you recall, they have to go where the plus exists. So this is going to be just the initial interaction. So I want to do this as kind of an analogy. Which side the H goes to is going to be like going to a theater. Let's say you go to a cheapy theater, you don't get to reserve your seats in advance. It's just first come, first serve. You and a friend go in. If you go in first, you're going to choose the better seat. If they go in first, they're going to choose the better seat. It's human nature. So same thing with chemical nature. This H is the first one to go on, and you have a crowded seat and a more spacious seat. So the H is naturally going to choose a more spacious seat and go on to the left carbon, leaving the next opening for the X, if it adds, to have to go to the more crowded. So we're going to refer to this eventually as something called Markovnikov addition. I'll write it down when the time comes. But it's the notion that the first thing to attack, first thing to interact, will always go to the more available carbon, less hindered carbon. Second one is going to resolve itself to go to the more crowded carbon. When it's a straight addition, they're always going to be on neighboring carbons. The plus one, the more electrophilic atom within the electrophile, the more positive, will go to the less crowded. The second one on, bigger one, will go to the more. Okay, that said, just want to see the big picture here. What we've done is we've, in essence, done the opposite of elimination. Before we eliminated the H, it was anti, so this is sin, but I'll just ease of drawing it. The electrons go in. When we deprotonate, kick out the X, and end up with a double bond. This is just a reverse. Okay, so some of the other eliminations we did, we eliminated alcohols, protonated them, OH left, and we ended up with an alkene. So we can also do the reverse of that reaction. We can take an alkene and add water. Now we have to add acid in order to make this go on, and H of water isn't reactive enough for the carbon to attack it. So although it's still a delta plus, and that is the group that'll be attacked first, you need to catalyze it with some acid. So if this carbon, these pi bonds can, or pi electrons can go over and pick up the H, and this carbon can pick up this H, then the OH ends up on the more substituted, more crowded carbon. So it's the same thing we saw above. It's still going to be Markovnikov addition. But I also want to introduce, just not like you don't have enough terminology already, but add a little bit more. Hydration reactions, as the name implies, hydrating is to add water. So hydration of a pi bond results in an H on the less crowded carbon, OH on the more crowded carbon. Very common reaction in biology. We hydrate and we dehydrate. So the forward reaction, the addition reaction, is hydration. The reverse reaction, elimination, is dehydration. So your job is to recognize just what's going on and coming off the molecule at the biology level, and then the OChem level, you need to focus on how it happens, exactly how the electrons are attacking, what groups go on, and then how you can, if you make small changes, how you can adjust what you get as your final product. Okay, so two reactions to start, just the addition of HX, H, an acidic H, and some group, leaving group as I'll call it, that it's attached to, and then that becomes a nucleophile to add to the carbon down the road. Okay, so want to look at this thermodynamically. So the equilibrium between what you're starting with, in this case we started with the alkene and the HX, and in the end we end up with the alkyl halide, whatever chain length this is. So it's going to be variable. So I'm just saying alkyl halide. We have to decide if it's favored to go in the forward direction or the reverse direction. And it's not actually an equilibrium. So I need to qualify this, that it's an equilibrium for any reaction, but the forward reaction will have a certain equilibrium and the reverse reaction will have a certain equilibrium, and our conditions will dictate which one occurs. So I'm still going to treat it like an equilibrium because the forward reaction is in equilibrium, reverse going to be in equilibrium, but I might change some of the conditions for this. So let's first look at the thermodynamic factors. We have two molecules on the reactant side. We have the alkene and HX, and the product side is drawn, we have one molecule. So for the forward reaction, delta S is going to be negative. It's entropically unfavorable. Reverse reaction, delta S will be positive. So let's just consider the forward reaction for now. So I have my delta S, it's negative, unfavorable forward reaction. And then you have the delta H component. So in this case, you're breaking a pi bond and breaking an HX sigma bond. An acidic sigma bond is kind of weak. That's why they break so easily. So I have a weak sigma bond, I have a weak pi bond, and I'm forming a stronger sigma bond, carbon H is pretty strong, and a carbon X bond, which is a medium strength sigma bond. But the point being is I'm breaking weaker bonds to form stronger bonds. So I'm going downhill. So delta H will be negative in that case as well. So if you recall from the equation, delta G, the free energy change of a reaction, equals delta H minus T delta S. Then we have this battling issue here. We have a negative for this. If S is negative, minus and minus is plus. So the question is, which is more predominant, the delta H factor or the delta S factor? So 2 to 1 molecules or 1 to 2, that's a significant entropy change. But breaking two notably weak bonds to form notably strong bonds, that's a pretty significant delta H factor. So the temperature actually is going to be our most important factor in what we're looking at here. So if we carry it out at high temperature, then this is going to be unfavorable. So delta S is negative, so minus and minus is plus, temperature goes up, it's plus a large amount. So negative number plus a larger positive number, or plus a larger number, I should say in general, is going to lead to a positive delta G. So at high temperature, it doesn't want to go forward. So for the forward direction, we want low temperature, or if you will, room temperature. To get elimination, we already learned this last chapter, we prefer high temp, and here's our rationale for it. As soon as you heat it up, you can overcome the entropy factor, or the entropy factor becomes more significant. You can overcome the enthalpy factor. Plus, just according to Boltzmann's distribution, the more you heat it up, the more it goes to the less stable compounds. Just and I'm going to be careful saying less stable because we don't know exactly what X and H are. Well, we know what H is, but we don't know what X is. But generally speaking, high temp is going to go back that way. So for this reaction, again, there's our equation. We find that delta G at less than 0 at low temp. So that means addition reactions can be done at room temperature. It should be. And then going back, elimination needs heat for best results. So I'm going to go ahead and get rid of my delta G equation. So you can clearly see. But that's our basic gist here. So just to mention it, you need heat to get elimination and room temp to get addition reactions. Okay, just want to toss it out there because it's kind of weird that in one chapter we're teaching you that, oh yeah, we can eliminate and form this product over here. And then now I'm teaching you in one chapter later, oh yeah, but we can also add. So it's not we're going schizophrenic. We're going to find that there's a lot of pathways that can go forward and backwards. This is going to be a theme, definitely when you get to biochem. It's going to be a theme in OChem, synthetic pathways where you make something or you break something. Either way, we're going to have the same basic gist is going on in all science. We're going to take advantage of forward and reverse reactions for our needs. Okay, so I want to continue on. So the hydration reaction equilibrium, same story as before, only this time I'm going to take advantage of the equilibrium, not just with temperature, but also in this case with the amount of water we put in. So if you recall, equilibriums can be shifted by adding reactants. So let me just do a quick insertion of an A in there. So because water is a reactant, it's going to go forward. So if I use strong acid to get this reaction going, to protonate here, create a carbocation, and then water can attack it. With strong acid with water, adding a reactant, can push the reaction in the forward direction. But in order to push it in the back direction, we just are going to use pure acid. So in this case, the reverse direction is concentrated acid without the water. That means without water, it's going to go in this direction to regenerate the missing water. So as long as I keep driving water off, I can keep pushing the reaction back. So this truly is kind of an equilibrium. So if I heat it and drive the water away, we get elimination. If I add water, do it at room temperature, and use a strong acid, we can do hydration, or addition of water across the pi bond. Okay, this is important if you're going to go into lab and figure out how to push reactants along, is that sometimes we can force a reaction that doesn't want to go by just pounding it with way too much reactant. So in order to push it in the forward direction, I keep adding one reagent, so I douse it so much that it forces it to go. And then I collect my product and drive my product off, which makes more go. Drive my product off, more can go in that direction. So the addition of reactant or removal of product will help push a reaction in the direction you want. So adding water will help push it forward, removing water will help pull it backwards. So just revisiting some of your GChem. Okay, so one of the things that's going to be really important in this chapter, a ton of information. I mean, literally over 30 reactions will be thrown at you in a very small window of time, and it can get incredibly overwhelming. So from day one, as we start looking at reactions, it's imperative that you get highly organized with how you look at things. So I'm going to refer to it as a spider chart. I like to actually call it a clock chart, but standard convention is a spider chart where we start in the middle and web out. I like the clock one because you say the 12 o'clock reaction, 1 o'clock, 2, 3, by just drawing reactions from it. But we're going to start with a molecule in the middle. Notice I've started with an alkene because this is the alkene chapter. And also, I've intentionally chosen something that has asymmetry. 2 R groups on one side, only 1 on the other. So we have a more crowded and a less crowded side. So the first reaction I want to talk about is hydration that we just did, where we said if you add acid to make the reaction go, and water, you can add across a double bond. Acid, H plus, is the most reactive species here, so it will go on first. The H goes to the less crowded carbon here, which forces the water to add there and eventually get deprotonate and turn into an alcohol. So I put the dash line here. I could have easily put it in the forward spot. It ends up there is no chiral center here, so it's kind of a moot point. These should just be two straight lines. But I'd like to do that just to emphasize that it did go on, and the CH3 was moved out of the way. It went from SP2 to now sticking out in an SP3 fashion. So I did not draw this for chirality purposes. I drew this for three-dimensional perspective. The other actions that we're going to do is we're going to add an HX, just as we did before, but this time I'm choosing a different solvent than water, because water, we know if we add acid and water, we can potentially get this alcohol. So to avoid the problem of getting an alcohol, if you don't have water, you don't have to worry about it. So we use carbon tetrachloride, which is a terrible nucleophile, which means when the H goes on first, and I have the same carbocation I just had here. So again, we're adding an acid to begin with. So H goes on first and makes this carbon available. Water was your better nucleophile, and there was lots of it, so that's what came on in this reaction. Br minus isn't necessarily a great nucleophile, but it's the only nucleophile in town. The CCl4 is not a nucleophile. H is an electrophile. It's been added on, so the Br minus that's generated when you deprotonate HBr is going to come in and attack that carbon. So in essence, you're getting the same structure. And again, not a chiral center, emphasizing the sp2 nature of this turning sp3. One thing I should make note of is I'm showing the OH adding in back, the Br adding in back, because it is planar, it can attack from top or bottom. So the Br could be in front, CH3 and back, or vice versa. Again, it's not a chiral center, so I can't actually prove that it did one or the other, because they're the same molecule. But half the time it's going to come in back, half the time in front. So this ongoing spider chart is just a generality. H2SO4 is preferred acid because the conjugate acid, HSO4 minus, is not a nucleophile, so water is preferred. But you could do this with another acid if you wanted to. Same thing here, HBr is what I'm choosing to put on a Br, but if I did it with, for instance, HCl, I get a chlorine. If I choose a different acid, it may or may not be strong enough in CCl4. So I have to consider those factors, but I'm not locked into HBr. And so know that this generically represents other potential additions, iodide and chlorine. But as long as it's strong acid in CCl4, I'm going to get that. I'm going to expect you to be able to recognize HCl instead of HBr, or HI instead of HBr in this. Okay, the spider chart, it's going to be ongoing. I'm going to keep adding to it throughout this entire chapter, and that spider chart is going to get really, really crowded very quickly. So there's going to be, I drew one at 3 o'clock and one at 6 o'clock. There's going to be reactions at 1 o'clock, 12 o'clock, 1:30, 3, 4:36, 7:39, and 10:30, meaning I plan on drawing 8 different reactions around it, and that still won't be enough. We're still going to eventually need a second one. But start it early and recognize what we're doing with it. Some more addition reactions. Again, this is not time for mechanisms, just generically looking at it. If I add 2 H's, what's interesting here is neither of these two are going to be delta minus or delta plus. So I'm emphasizing they're different H's by color, but they're actually identical. Which one goes on first makes no difference. And it ends up, because I'm adding 2 of the same thing, I couldn't tell anyway, but we're going to learn mechanistically down the road that they both actually add at the same time. So we'll address that later. Right now, I just want to measure or address what does add. So I got an H going on here and an H going on here. The color coordination, just make note of it. This could be there and that could be there, meaning I could just as easily have gotten the blue H here and the red H here. It would have been same thing. It makes no difference. But the key thing I want to emphasize here is we didn't hydrate. It wasn't water. We added hydrogen. So they call this hydrogenation. You absolutely, positively have to know this reaction for biology. Hydrogenation and dehydrogenation reactions are prevalent. In fact, a large amount of biochem is driven by NADH and then FADH2, which are reagents would help with the hydrogenation process. And again, you'll get to it when you get there, but know this reaction by name. So hydrogenation reduces the alkene from a double bond to an alkane. So it's more saturated. So again, whenever I say the word saturated, saturated with H. So hydrogenated products are ones that have been reacted with hydrogen, they've had hydrogen added to them, and they become more reduced or more saturated with hydrogens. Okay, one more to add to this, just like we can have two H's, we can also add two X's. And again, there's no difference between the two X's initially. So it could be ClCl, Br. We will learn if you did a Cl and a Br or something like that, that there will be the delta plus and delta minus aspect. And so this is maybe a little more applicable because X represents not just a single atom, but different possible atoms. But let's just think of it for now, at least, as two Cls or two Brs. Same story, this is going to come in, add one, get a carbocation, and the other one's going to go in. There's a few things in that mechanism that I will get to, but basically you add two X's. I've added an anti and want to emphasize this. So for the first time, I'm actually starting to give some hints about what we'll expect later. The previous two examples, there was no stereochemistry. Technically, there's no chiral centers here, so it's kind of a moot point because you can't verify it chirally. But do want to emphasize, because both of these add at the same time, these two H's, they both have to add to the same side. You can't really add one to one side and one to the other without twisting the molecule into a form it won't go. So when it's simultaneous addition of both atoms, both groups that are going to the two carbons of double bond, they add in what's known as a syn addition fashion. They add to the same side. When you add them one at a time, which happens with X2, with halogenation, so Cl2, Br2, when I add to an alkene, the first one will go on one side. When it goes on one side, so let's say the X goes on the top side, it makes the bottom side more available to attack, so that the X has come in from, the second one has come in from the opposite side. So they end up in an anti-addition. So syn addition, when you add both at the same time, when you add them one at a time, you get what's known as anti-addition. One goes on, and the other one goes on from the opposite side because the first one on makes this side more crowded, which favors the lower side. Again, this will make more sense as we go, but just something to pay attention to. The reason I did the two H's on the same side here and X's on the opposite side, this is known as syn addition. So let me get rid of this. So this is known as syn addition. This is known as anti-addition. You're going to hear these words a lot in this chapter. Okay. So simple addition mechanism, I want to figure out how this actually happens. So we mentioned that it involves the pi bonds as the nucleophile coming and attacking an H and the Br becoming negative. So when that happens, trust the purple drawing here. So it comes in, picks up the H, those pi electrons go there. You now have H added. So you have this formed here. So here are my two H's, check. My two H's over here. These electrons went over here, so the H goes here, and you're left with a carbocation. So primary carbocations are unstable. This is highly, highly unlikely to occur, but still going to do it as a generic example. That's also why I put CH3s on the previous one. So then if we made it secondary or tertiary, it'd be more feasible. But let's go with this primary carbocation. The Br minus that you kicked off is now floating around. And so the Br minus that is here can have its lone pair, any of the four, come in, attack the carbocation. And when it does that, you form a new bond. So this is my addition across it. Didn't necessarily mean to do a Fisher projection sideways, but it is what it is. And because it's not chiral, I don't really care too much where I put the various atoms. But the key thing is we've added an H to one of the carbons and a Br to the other carbon. Mechanistically, H goes on first to the less crowded site. There is no less crowded in this case, but if there were, H would go to less crowded, carbocation would be on the more stable, so the Br would go to the more substituted carbon. So it's a simple mechanism, and you're going to find that most reactions follow something like this when it's one at a time addition. So we add first the H, then the Br. So for anti-addition mechanisms, it's almost always the case where one goes on the less crowded side, second one comes into the more crowded side. Okay, so what if it is asymmetric? This is a huge crux within what we're going to do the next month at least. when it is asymmetric, meaning I have two R groups on this side and only one on this side. So in this case, this is a tertiary carbon, if you will. This is a secondary carbon, if you will, two other carbons attached. Because we have them in an alkene, it's not typical that you refer to as secondary, tertiary, but that's ultimately what it's going to be. So I'm going to concern myself with that. The H will go to the less hindered, the one that has an H. So a famous phrase from the immortal and brilliant chemist Forrest Gump, H goes where H is. And if you can always say that, pick the side that already has an H. So right here we have an H. So no H's over here, one H on this side. So H goes where H is. And you'd have to have seen the movie to understand the reference in the accent. So hopefully you have seen it. But as Forrest Gump would tell us, put the H where you already have an H. Okay, so these two H's go together. You now have this carbocation. This Br is going to come in to the carbocation site, with this product. It's the exact same reaction we just did with the ethene, with the 2-carbon alkene, only now we have distinct crowded, more crowded and less crowded sides. Okay, so H goes on first and chooses less crowded carbon. That's key. We get this. This is what's known as the Markovnikov product. So it's called regioselectivity. So it's a new term we're going to add. There's going to be two, regioselectivity and stereoselectivity. Regioselectivity tells me what region of the molecule does it choose, which in essence, does it choose the left carbon or the right carbon? Markovnikov is where the more crowded or larger group goes on the more crowded carbon. That's what it's referred to as, the more substituted carbon. But it really is as simple as H goes where H is. First thing to go on goes to the less hindered side, leaving the second thing, the bigger thing, to go to the more crowded or more substituted side. So Markovnikov addition gives you the bulkier group on the more substituted carbon. Stereoselectivity. So stereoselectivity refers to which side does it add to? Do I get a chiral center as a result? So let's just look real quickly and see. We add an H where H was, so we have two identical substituents, so no chirality there. This is sp2 hybridized. It's an empty p orbital, so the Br could come in theory from on top or on bottom. But because this group, CH3, is identical with this group, CH3, these two are identical, we don't have a chiral center here, so it's not applicable here. There's none in this case. Doesn't mean we don't have to worry about it. Usually you end up getting a racemic mixture from these if you have no initial chirality. And if you have a chiral center somewhere in there, you usually end up with diastereomers. So there is stereoselectivity associated with this. We just happen to do an example where we have identical R groups, so it doesn't matter. But if they're not identical, then it mattered. So if this would have been an ethyl, this would have been a methyl, then we would have got equal parts R and S. But in this case, no chiral center to worry about, so no stereoselectivity to make. So for every addition reaction, you're going to have to first figure which carbon does the bulkier group go to. My regioselectivity, is it Markovnikov or anti-Markovnikov? And which side does it attack, top or bottom? So do I get R, S, or a mixture of R and S at that center? And that will be your so-called stereoselectivity. Two-step reaction, H goes on first to the less crowded carbon, leaving Br to go on to the more crowded carbon. So it's more spider diagram building. So we have two more reactions to add in. So I want to add the word Markovnikov here and Markovnikov here. So I want to add my details. And then I also want to add in hydrogenation. Apparently I'll be adding it in the future to the spider diagram, but just adding the word Markovnikov. We're going to make room on that diagram for adding X2 and H2 as well. So I will see you at the next video. I will space this out as best as I can and hope that you have an absolutely wonderful action-packed day. And I will see you at the next recording.